Thank you very much for inviting me to this talk. So firstly, this talk is about compression of Macdonald polynomials from alcove work formula to the Hegel-Hamer law formula, comparison of different Macdonald polynomials. So in this talk, we will be separated into three parts. Firstly, I'm going to talk about the non-symmetric Macdonald polynomial. In terms of the double alpha Hecke algebra, which we shorthanded to be the DAHA. So then I'm going to introduce our main result. So here it's the main result. So it's theorem 1.1 in our paper. So it states that the non-symmetric Macdonald polynomial can be written as some sum over alcove works with their weights. And we call this the step-by-step recursion. And I will explain what those are later. So, and secondly, we can denote that non-symmetric Macdonald polynomial is summed over some non-attacking fittings with their weight. And we denote this the box-by-box recursion. And lastly, I'm going to talk about one example of how we perform the box-by-box recursion. Okay. So let us first look at the double alpha Hecke algebra, which has generators and relations. So the generators, oh, by the way, so this work is joined with Arun Ram. So I think who have given a talk just previously. So the double alpha Hecke algebra is generated by generators Q, G, G check, and S0, S0 check, T1, Tn minus 1. And there are a couple of important relations, but we're only going to state a few of them, which is easier to state. Firstly, those those diagrams with T1 to T2, Tn minus 1. So those are the bread relations, and we have the second bread relation look like this. And we see that the diagram just means that if we have an edge between two vertices A and B, then we can have ABA is equal to BAB. And if there are no edge between two vertices A and B, then we will just have AB equals BA. So they commute. And lastly, which is quite important relation, is that Ti plus T to the minus half times Ti minus T to the half is equal to 0. So we choose the normalizer to be T to the half in this case. And there are some more relations which I'm not going to state in this talk. So inside of the double alpha Hecke algebra, there are some operators which are called Yi's. So Y1 is denoted to be G check Tn minus 1 to T1, and Yi plus Y is denoted to be Ti minus 1 Yi, Ti inverse, and this is for 1 to n minus 1. And we have also some intertwiners, which is called tau I check, which we denote it to be Ti plus 1 minus T, 1 minus T, we have the bracket here, T to the minus half, 1 minus Yi inverse, Yi plus 1. And we also have tau pi check, which is simply G check. So any questions about those relations and operators? Well, if not, we should continue. And by the way, so we can also interpret this as Ti inverse to be T to the minus half, 1 minus T times Yi inverse, Yi plus 1. 1 minus Yi inverse Yi plus 1. Sometimes this is quite useful inside of the double alpha Hecke algebra. So this can be obtained by written Ti by using the relation just here. So we have it here. And we can apply this to here and get the inverse relation, which sometimes can be useful in the computation. Anyway, so one of the important subalgebra inside of DAHA is called the affine Hecke algebra. So the affine Hecke algebra, we denote it as AHA. So it is generated by y1 to yn and t1 to tn minus 1. So it's a subalgebra of the double alpha Hecke algebra. So this will play an important role when we define the polynomial representation of double alpha Hecke algebra here. So the polynomial representation, which is an interesting representation to look at for DAHA. So it's the Laurent polynomial cx1 plus minus 1 to xn plus minus 1. And it is induced from the AHA to the double alpha Hecke algebra with the trivial representation of the alpha Hecke algebra. And we can write in terms of the C-span of x mu acting on identity, which mu is belong to Zn. So mu is basically some thing look like this, if we want. So now we are ready to define what are non-symmetric Macdonald polynomials are. So non-symmetric Macdonald polynomials, we can write it in terms of t to the minus half length of v mu inverse times tau u mu check. So with the intertwiner acting on the trivial representation. And this thing, actually by definition, they are simultaneous eigenvectors of y1 to yn on the polynomial representation. So in here, we are just given an explicit formulation of the non-symmetric Macdonald polynomials. And I'm going to explain what those v mu and u mu are later in the talk. I mean, just one slide down. So there are some inductive ways to construct those non-symmetric Macdonald polynomial. So namely, we can define, I mean, it's given that with mu equals 0, 0, 0, and the non-symmetric Macdonald polynomial E0, 0, 0 is just 1. And we can recursively or inductively define E pi mu, so which will give us t to the minus, t to v mu n minus 1 plus a half n minus 1 tau pi check acting on identity. And we can also get si mu, and we get ti plus 1 minus t times t to the minus half 1 minus q mu I minus mu I plus 1 t to the v mu I minus v mu I plus 1 and acting on v mu. So those operators pi mu and si mu simply will switch the order of mu. So pi of mu 1 to mu n will give us mu 1, so mu n plus 1. So it will rotate and add 1. So this is n minus 1. And this is the action of pi acting on mu 1 to mu n. And the action of si mu is just simply switch the position I and I plus 1. So inductively, we can construct E mu just by those two operators and from this. Any questions about this?
I'm sorry, just to make sure, pi acts on a partition just by shifting and getting nth to the first position and adding 1. And so the idea is that we take it for 0, we get 1, 0, 0, 0, then we can do all the possible switchings, and then acting by pi's and simple reflections, we get all of them.
That's right.
Thank
you. Okay, so next we're going to talk about the elements v mu and u mu appeared in our non-symmetric Macdonald polynomials. So they are quite important elements in our paper as well. So firstly, this v mu element is inside of our symmetric group Sn, and it satisfies two conditions, which is quite interesting. So firstly, it need to be minimal length. So the length in our case is the number of inversions. And secondly, we require to be, so v mu acting on mu is weakly increasing. So let's see an example for mu equals 2 to 1, 1, 0, 0. We have v mu is basically 5, 6, 3, 4, 1, 2 in one line notation. So we switch 2 to the first, no, the second 2 to the 6th position and the first 2 to the 5th. And we keep those ones at the same, and we will obtain a one-line notation in permutation notation. And pictorially, we can view this as, well, 1 goes to 5, 2 goes to 6, 3 goes to 4, 5 goes to 3 goes to 3, 4 goes to 4, 5 goes to 1, and 6 goes to 2. And we can also do this with the simple transpositions, which is basically switch S2, S3, S4, S5, and then we apply a series S1, S2, S3, S4. Now we arrive at the sequence 1, 1, 0, 0, 2, 2, and then we have to switch 1 to the 4th, so we'll get S2, S3, and then S1, S2. So at the end, we have the length of v mu is equal to the length of v mu inverse is equal to 12, which is the number of transpositions occurred here. And it also is the same as the number of crossings in terms of these diagrams. So there are crossings here. So let's continue. So this is the element v mu. And now we will start talking about the element u mu, which is also an interesting element in terms of generating the non-symmetric Macdonald polynomial. So before I introduce the element u mu, we will actually talk about where it lives. So the affine Weiying group, also known as the n-periodic permutations. So n-periodic just means if W omega or W is inside of our alpha Weiying group, then we'll get W acting on I plus N is just Wi plus N. This is n-periodic permutations. And there are basically two presentations of this alpha Weiying group. And one of them is, so W is equal to the semi-direct product of Zn semi-direct product with Sn, the symmetric group. So it can be written as T mu acting on V, where mu is inside of Zn and V is inside of Sn. So in this case, T mu acting on I is just I plus N mu I for I from 1 to N. And the second presentation, which is also quite interesting, is with generators and relations. So it can be generated by S0 pi S1 to Sn minus 1, where S0 is defined to be epsilon1 check minus epsilon n check. And we have Sn minus 1 to S1, S2, S1, S2, Sn minus 1. So in terms of the relations, we will get pi Si plus 1. Sorry. Pi Si, pi inverse, we'll get Si plus 1 for 1 to n minus 2. And pi Si, pi Sn minus 1, pi inverse will give us S0. So any questions regarding to these presentations of the affine Weying group? So those t epsilon 1s are actually just T1. So if you actually T mu in terms of the composition, mu is equal to mu1 to mu m. And then T mu will just be T mu1 epsilon 1 check plus T mu n. Sorry, this multiplication. T mu 2 epsilon 2 check T mu n epsilon n check. So they add up.
In this second presentation, for the first relation, should that include I equals 0 as well?
Yes, that's right. All right, thanks. So if no more questions, then we should proceed with the affine Weying group. So the interesting element U mu is some element inside of our affine Weying group, which is also the n-periodic permutations. So the affine Weying group W can be written in terms of the generators. It is generated by pi S1, S2, Sn minus 1. So we can discard S0 in this case because it can be replaced with S1 to Sn with the action of pi. And then the element U mu belongs to the affine Weying group, which is defined to be T mu V mu inverse. So V mu is now the minimal length element. Again, we remind ourselves what V mu is. So such that V mu mu is weakly increasing. And we can, in particular, choose some reduced word. For example, SI1 to SIR. For IK is inside of pi 1 n minus 1, whereas pi is just pi equal to pi. So one of the interesting choice of the reduced word is called the box-greedy reduced word. So for this U mu, where we put a box on top of the U mu, and this is product over the diagram of mu, which I will explain later what those diagrams are, which are in terms of the simple transpositions is a product over S U mu ij times S1. And those U mu ij is basically the non-attacking boxes, which I will also explain just in a minute, of a box ij. So this is a particular reduced word for U mu. So one of the choice which I made, or which we made. So let's see how we actually obtain this U mu box, and then we will explain how those attacking boxes, what are those attacking boxes, and what those diagrams are. So to obtain this particular choice, for example, for our mu equals 2, 2, 1, 1, 0, 0, we can actually, using the process which we call unwinding mu. So we apply a pi inverse. So the action of pi inverse does this. And we apply pi inverse again, which each time we remove 1. So we apply a pi inverse again, we get this. And we apply pi inverse again, we get 0, 0, 1, 1, 0, 0. And then now we see that the first position is non-zero. So we apply S2, S1 pi inverse to switch the 1 up to the front, and we get rid of it. And then we apply a series of this again, we get 0, 0, 0. And so in terms of U mu or U mu box, we'll get the reduced word is pi, 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 pi. So each time we remove a box. So if you want to think like that, so we'll get this. And then the diagram is simply dg mu. In this case, is just this partition. So it look like this, which we have 2, 2, 1, 1, 0, 0. And then we have tau u mu check or tau u mu box check, which is tau pi check, tau pi check, tau pi check, tau pi check, tau 2 check, tau 1 check, tau pi check. Sorry, you might not be able to see this. So I'm trying to describe this tau u mu check here. So in terms of u mu check, we'll get tau 2 check, tau 1 check, tau pi check as the reduced word. And so for the attacking boxes, in this case, if we have a box saying 2, 2, so in the second row and second column, and the attacking boxes are basically the consecutive end boxes which intersects the diagram. In this case, it is just those boxes here, which there are 3. And in this case, we have n equals 6. So apply this formula, which is 6 minus 1 minus 3, which gives us 2. So we see this is exactly the 2 corresponding here. So indeed, we can also see why we call this the box Grady reduced word, because, well, if you fill up your diagram, so it takes a bit of time to remove this. So if you fill up your diagram with pi, 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 S2, S1 pi, S2, S1 pi, we see that each time we are actually getting rid of one box of the diagram, mu. Any questions? So this reduced word will indeed leads us to the compression or the compression formula from the alcove work formula to the non-attacking filling formula of our main result. So before talking about our main results, I will actually generalize the non-symmetric Macdonald polynomial a little bit to the so-called permuted basement Macdonald polynomial, which is also known as the relative Macdonald polynomial in our paper. So those permuted basement Macdonald polynomial is denoted by E mu z, which is t to the minus half length of, so length of z b mu inverse minus length of mu inverse with tz times E mu. And this z is simply inside of the symmetric group Sn. And when we set z equals identity, then we should recover that E mu z is simply E mu. So we will get our non-symmetric Macdonald polynomial when specializing z equals identity. And we also remind ourselves that those non-symmetric Macdonald polynomials are actually simultaneous eigenvectors of those y1 to yn on the polynomial representation. So I think now we should make a little break. So any questions with regarding to the first part of the talk, you can probably ask now. Otherwise, I will proceed into the main result of the paper.
Hi, Weiying. This is Siddharth Sahi.
Oh, hello.
Hi. I just had a comment. So I said this to Arun, but maybe I should point it out to you. So exactly this recursion that you're describing plays, or this reduced word that you're writing, this plays a key role in my paper with Friedrich Knopp. So I don't know. I mean, it's
Right.
It's lemma 4.4 or something.
Yeah,
Exactly.
Yeah. So this your recursion, the Nufsahi recursion. Yes.
Yes. But yeah, so yeah, it would be interesting to understand, what is the relationship of this with the recursion formula, because there's some canceling of denominators there also for Jack polynomials, which was kind of the point of our paper.
Yeah. So the point was that for the box by box recursion, which I'm going to talk about later, where we grouped the, I mean, it's also happening in Christine Lina's paper that if you group those things together, then there's cancellation occurs.
Yeah, there's some cancellation of denominators. If you move something past a whole bunch of zeros, then there is some there's some cancellation of denominators. So
Yes.
Friedrich, kind of. So it would be interesting to understand what's the relationship of this. Okay, that's all. It's not really a question. It's just a comment.
Okay, so if there's no other questions, then we should proceed into the main result. So the main result of our talk, of this talk, is about theorem 1.1. So basically it separates into two parts. Firstly, the permuted basement Macdonald polynomial is summed over some weights, which is over the alcove works, which we call this the step-by-step recursion. And the second part is the box-by-box recursion, where we sum over some non-attacking fields. So let's see how those statements are related. So let's write this formula again. So for the permuted basement Macdonald polynomial E mu z, it's basically summing over some alcove works, which we call the P of type mu z of their weights, P to the weight of P. And the weight of P is actually some product over each step. So I equals 1 to R weight of P to the K. So this is K. So if we choose some particular reduced words, let's say the box is SI1 to SIR, and then we will get this. And then secondly, we have the non-symmetric Macdonald polynomial is sum over some non-attacking fields with mu z with their weight of T. And the weight of the non-attacking fielding is again defined by box. So we sum over some box inside of our diagram with the associated weight of each box and product over it. So now let us look in detail about how those alcove works are, what are those alcove works really are. So the alcove works are actually defined. So the alcove works AW mu z is the set of alcove works of type Z U mu box, let's say. And then for each U mu box, we can choose a reduced word called SI1 to SIR, and they are corresponding alcove works, which is a sequence of P1 to Pn. or let's say P1 to PR, sorry, where PI is inside of our affine while group. So this is the affine while group we have been discussing, and periodic permutations. And then for each of them, we have P. So P0 is equal to Z. So we require the first one to be the Z. So Z is some permutation inside of Sn. And then we require Pk to be Pk minus 1 times pi if Sik pi, if Sik is equal to pi, and Pk is inside of Pk minus 1, Pk minus 1 times Sik, if Sik is not equal to pi. So basically there are consecutive steps of works, whether it's either a crossing or a fold or some pi, which is some diagonal work. And now, so about this main results, the first part we have not really defined, and we are probably not going to define it in full for the remaining of the talk, is the weight. So the weight is given by this, which is separated into 4 cases, which each of them corresponds either to a positive fold or negative fold, or crossing, or actually a pi. And they are related to these statistics of the affine co-roots. But the most important thing is that in the proposition 4.1, we see that the proof of this first part of theorem 1.1 is rely on proposition 4.1. So if we have mu1 is not equal to 0, then we will get a recursion look like this, where we get an extra factor of xz1, and we also remove a box here. So we see that we get mu1 minus 1. And this xz1 corresponds to exactly the xzk minus 1 here, with the case where we have a pi. And then if we have mu1 is equal to 0, then we've searched for the minimal I such that mu I is less than mu I plus 1. And then we will be separated into 2 cases. Each of them corresponds to zi less than zi plus 1 or zi greater than zi plus 1. And we see in the first case, we get a 1 and the extra factor look like this. And the 1 corresponds to exactly this weight in our formula, and the extra factor here corresponds to the positive fold factor we have in here. And then for the second part, we have again a 1 here, which corresponds to a crossing, and then the extra factor, which corresponds to a negative fold in the second part of our weights. So any question about this? So if not, we should proceed to the second part of our main theorem, which is the box-by-box recursion. So in this case, we look at a step-by-step recursion where each part is just each time we are doing a step. So in terms of intertwiners, we are just doing a SI in this case, and then in this case, we are doing something like a pi. So we have a tau pi here and a tau I check here. And now we are looking at how we group how we do the box-by-box recursion on the non-attacking fittings. So which is the second part of our result. So the second part of our result is box-by-box recursion. And let's first define the non-attacking fittings. So the non-attacking fittings are basically we require the basement, so Ti0 to be Zi. So for example, if we have mu equals 2 to 1, sorry, mu equals 2 to 1, 1, 0, 0. Then our basement and z equals identity, let's say, so it's element in Sn. Oh no, in this case it's S6. So we have the basement is just 1, 2, 3, 4, 5, 6. This case, and this is the basement, and mu is the diagram look like this. So we require the basement to be exactly the same as Zi. In this case, it's just identity. So this is the basement. And now if we take some box, call it A, let's say B inside of our diagram mu, and we have A in the attacking boxes of B, then we require the filling to be different. For example, in this case, we have a non-attacking filling look like this. So this is a non-attacking filling. We see that the box, this position, the box with 1 here is basically not the same as 2, 3, 4. So they are non-attacking. The attacking box have all different fillings. And we have the box containing 5, all have 5, 1, 3, 4, and they also have different fillings. So this is the basic idea of non-attacking filling. Any questions about the non-attacking fillings or other stuff? So if not, did anyone say anything? No? Okay. So if not, let's look at a little bit of how we define our box, our weights in terms of our results. So the weight is some product over some boxes in the diagram. So remember that the diagram is of mu sometimes just looks like this, or all the time it looks like this. For mu equals 2 to 1, 1, 0, 0, it looks like this. And we product over some weights of the box. And the weights separate into 3 cases in this time. So the first cases is where we have a, this is a ascent, and then we have a descent, or we have the filling of the box are actually equal. So those three cases corresponds to the 3 cases of the filling of the box. And we see where the descent and ascent separates with only the factor here, which is the same as we had in the positive fold and negative fold. Now let's look at a little bit about the proof of our box by box recursion, which is stated here. So let's see. The important factor is that each time we are actually removing a box. So for example, for mu equals 0, 0, 0, mu j, some type of mu look like this. And then we define that gamma to be 0, 0, 0, and mu j plus 1, mu n, and mu j minus 1. So we remove a box here. So in this entry, we have removed a box. And then in this term, then we will get the recursion look like this. And so each time we removing a box, we will get, so each time we removing a box, so we do a 1-step recursion, remove a box, we'll get either an extra factor of x, y, j, which corresponds to one of the weights in here, where we have the filling are the same. And then, or we have a extra factor like this, which depends on whether we have a ascent or descent in terms of our major statistics or COVID or co-inversion statistics. So in terms of this, we will actually have a look about how we define one of those statistics, which are interesting. So that's the major statistics, which is easier to carry out. So the major statistics is defined to be 0 if zj is greater than za. So in this case, we have a descent where we see correspondence as very clear. So is when we have an ascent, sorry. So if we have a descent, we will just get mu j. So zj is less than za. So in this case, we'll get zj is tn bn minus, where we get a descent here. And we see that the major statistics corresponds to exactly those number of non-attacking legs of the box. So where we have not really defined here, but here it is corresponding to these statistics. And this makes the separation of those two statistics into the two different cases in terms of those weights. So it depends on whether it's ascent or descent, we'll either get the above one or this one. Any questions regarding to this? So if there's no questions, then let's continue to see an example of our box-by-box recursion. So let's bring out our favorite example throughout the talk, which is mu equals 2 to 1, 1, 0, 0, with z equals identity 1, 2, 3, 4, 5, 6, which we have been discussing before. So in terms of this example, we see that the first case where j equals to 1. So j equals to 1 in here. So because the first position is non-zero, so we have j equals to 1. And therefore, we have only this factor for the first step recursion. And the remaining factor, this is j minus 1, which is 0. So we don't have this factor. Therefore, for this first step recursion, we get x1 e2110001 and corresponds to the non-attacking fielding. We get a 1 inside of our non-attacking fielding. And for the second recursion, we see that again, j equals to 1 because the first position is non-zero. And we get x1, x2 here. And then we continue to do this until the first position is 0. So we get a fielding with x1, x2, x3, x4. And this corresponds to the non-attacking fielding look like this. And then the remaining part will keep expanding. So in this case, the remaining part corresponds to how we fill out the remaining two boxes in the non-attacking fielding. So to expand the remaining part, we see that in this case, j is equal to 3 because the first position is 0, the second position is 0, and the third position is non-zero. So it is interesting because we need to expand the full recursion now. So to expand the full recursion, we see we had 3 terms in this case. And we have 3 terms, and collecting those 3 terms, we will get some expansion like this. And we can continue copying down this expansion, and we collect all of those expansions for u22110. So we plugged this expansion into this expansion here to obtain the first 3 expansion of 221100. We'll get the first 3 terms look like this. And those corresponds to exactly the non-attacking filling 1, 2, 3, 4, 1, 2 for the first one. You see this is the filling. And then for the second one, we have 1, 2, 3, 4, 1, 2, 3, 4, x1, x5, which is exactly the one I mentioned just in the middle of my talk, which is 1, 2, 3, 1, 5. And the last one is 1, 2, 3, 4, and 1, 6, which gives us the non-attacking filling look like this. And this is the end of my talk.
Okay, let's thank Weiying. Yeah, I think I'm gonna stop recording.